This bridge is about to tear itself apart, and the wind doing it isn't even a storm. November 7th, 1940. The Tacoma Narrows Bridge is 4 months old, the third longest suspension span on Earth, and it is twisting like a ribbon in a 42-mile-per-hour wind. That's a brisk day. That's wind you'd barely notice walking to your car. This bridge was designed to survive well over 100. Within the hour, 600 feet of highway will be at the bottom of Puget Sound, and every engineer alive will have to admit they misunderstood something fundamental about air. Let's start with how it got built, because the failure was baked in before the first car crossed. In the late 1930s, Washington State wanted a crossing over the Narrows. The state's own engineers submitted a design with a deep, open, stiffening truss, a heavy lattice of steel under the roadway, about 25 feet tall. It was strong, it was also expensive, and the project was short on money. Enter Leon Moisseff, one of the most respected suspension bridge designers in the world. Moisseff had worked on the Golden Gate. He championed something called deflection theory, which recognized that in a long suspension bridge, the main cables carry far more of the load than older, more conservative methods assumed. Deflection theory was correct. It was also an invitation to build lighter, and the industry had spent 2 decades accepting that invitation, shaving weight and depth off deck after deck. Moisseff's Tacoma design replaced that 25-foot open truss with a solid plate girder, just 8 feet deep, slimmer, more elegant, cheaper by more than half, and structurally, for carrying weight, it was fine. The problem is that nobody at the time was asking the other question: what does this shape do to the wind? Because a solid, shallow, flat-sided deck isn't a truss. Wind can't pass through it, it has to go around it. And a body that wind has to flow around is not a bridge component, it's an airfoil. From the day it opened, drivers felt it. The deck rippled and heaved so persistently that people nicknamed it galloping gertie, and some drove miles out of their way just for the ride. Engineers were concerned enough to try fixes, tie down cables to the shoreline, hydraulic dampers, a professor from the University of Washington running experiments. The tie-downs snapped. The dampers were damaged, reportedly by sandblasting, during painting and stopped working. Nothing helped because everyone was treating the symptom emotion without understanding the mechanism producing it. So here is what actually killed it. This is the part your textbook probably got wrong. For decades, schools taught that Tacoma Narrows was a case of resonance. The story goes, wind hit the bridge in rhythmic gusts. That rhythm happened to match the bridge's natural frequency, and the vibrations built up like an opera singer shattering a wine glass. It's a tidy story, and it's in an enormous number of physics textbooks. It's also, at minimum, badly incomplete. Resonance requires an external force arriving at a fixed frequency that matches the structure's own. Steady wind doesn't provide that. What was actually happening is called aeroelastic flutter, and the difference matters enormously. In flutter, the structure and the airflow become a coupled system. Follow the loop. The deck twists slightly. That twist changes the angle the deck presents to the oncoming air. That new angle changes the pressure distribution and the pattern of vortices shedding off the deck's edges. Those changed forces happen to push the deck further in the direction it was already twisting. And crucially, they arrive slightly out of phase with the motion. So instead of resisting it, they feed it. Engineers describe this as negative damping. Normally, a structure bleeds energy out of any motion. It damps itself and settles down. Under flutter, the airflow is pumping energy in faster than the structure can bleed it out. There's no external drumbeat. The bridge is generating its own destructive rhythm, and the wind is just the power supply. Every oscillation makes the next one bigger. And there's a second condition that made Tacoma uniquely vulnerable. The plate girder deck was torsionally soft, weak in twist. Its bending frequency and its twisting frequency were close enough together that the two motions could couple into a single catastrophic mode. That morning they did. Around 10 in the morning, a mid-span cable band slipped, and the bridge switched from its familiar up and down, rolling into a violent torsional mode. One side of the deck rising as the other fell, edges swinging through something like 28 feet of travel, tilting to roughly 45 degrees. One man was still out there. Leonard Coatsworth, a newspaper editor, had been driving across with his daughter's cocker spaniel, Tubby, in the car. The deck's motion threw his car sideways. He got out, was knocked off his feet, and crawled on his hands and knees 500 yards to the towers, bruised and bleeding. He couldn't get Tubby out of the car. A professor tried and was bitten. The dog went down with the bridge, the only casualty of the collapse. At 11:02 a.m., the failure point arrived. A suspender cable snapped. Its load transferred to its neighbors, which were already carrying more than they should, and they went too. The pattern is called progressive failure. Each break makes the next one likelier, and the collapse accelerates. 600 feet of center span dropped into the water. The side spans sagged. The towers, pulled shoreward, were left permanently deformed. Now the part that redeems the story. How did we fix it? The wreckage became the most productive disaster in civil engineering history. Theodore von Karman, an aerodynamicist, not a bridgeman, was among those brought in, and the investigation forced a permanent merger between structural engineering and fluid dynamics. 3 things changed, and all 3 are still standard today. First, wind tunnel testing became mandatory practice for major spans. Engineers build scale sectional models of the deck, mount them on springs, and blow air across them to hunt for the flutter speed, the wind velocity at which that energy-feeding loop turns unstable. If the flutter speed isn't comfortably above anything the site will ever see, you redesign. Second, deck shape became a primary design variable rather than an afterthought. The replacement bridge opened in 1950, went back to a deep, open, stiffening truss, 25 feet, wind passing through it instead of around, and added grading slots in the roadway to relieve pressure differences between the top and bottom surfaces. Modern long-span bridges take the idea further, using streamlined box girders shaped almost like an aircraft wing, sometimes with fairings and vents so vortices never organize into a coherent driving force. Third, damping stopped being an afterthought. Big spans now carry tuned mass dampers and other energy-dissipating systems whose entire job is making sure the structure can bleed energy faster than the wind can add it. The 1950 replacement, inevitably nicknamed Sturdy Gertie, still stands. A parallel span was added in 2007, and every long span bridge you've driven across since was shaped in part by 4 months of a bridge that couldn't stop dancing. Tacoma failed because engineers optimized hard for a load case they understood, weight, while a load case they didn't yet respect was waiting in the air. But at least Gertie warned them. It shook for 4 months. It gave them every chance. 41 years later, in a Kansas City hotel, a structure would give no warning at all. It would stand quietly for a year with a fatal flaw drawn on a single revised page, and then fail during a dance. That story is next on this channel. Subscribe because every disaster has a failure point and we find it.